Hey everyone. In this video, before we start thermal energy in the next video, this is kind of a pre-topic that's pretty important to understand in order to understand the big topics in the next video on thermal energy. In this video, we're going to discuss something called the kinetic molecular theory of matter. I'm going to write that down. Kinetic molecular theory of matter. And we actually, believe it or not, learned about this in grade 9, but not in much detail, and it's pretty important for thermal energy, and I'm going to explain why. The kinetic molecular theory of matter basically describes how matter works and how it's constructed in our universe, how atoms and particles interact, and so forth. And it's made up of these 5 points that are important. So I'm going to go through each of the points and explain them in detail. Okay, first point in the kinetic molecular theory of matter is all matter is made up of tiny particles. I'm going to simplify these as I write them down. They're tiny particles. And in between these tiny particles, there are large spaces, large gaps between them. So here's a bit of matter, and it has particles, and notice there's a lot of space between them. The important part of this point is that despite how things that are matter look pretty solid, at a microscopic level, they're really not. There's a lot of little particles, but there's tons of empty space. So much empty space, you'd really be surprised. And this empty space plays quite important role in thermal energy and a lot of other things. The important thing to take away from this rule is that the spaces between the particles are much bigger than the particles. So there's actually a lot more empty space than there is filled space inside everything in the universe. Second thing, different substances, different things, have different types of particles. And this is kind of common sense. We've learned in chemistry about obviously different atoms and molecules and all sorts of things, and different things in the world are made up of different combinations of these. You know, the stuff that's in my bed sheets is a little different from the stuff that's in my lamp. The stuff that's in a book on my bookshelf is a lot different than the stuff that's in my tablet. Can you tell I'm in my bedroom? Yeah. That makes a lot of sense, and it doesn't connect so much to thermal energy, so it's not the most important one of these 5 things. Number 3. Particles are always in motion. They're in constant, random motion. And there's 2 adjectives there, constant and random. Constant means that they never stop. Particles always move. It's all they do. Even in a thing which looks kind of solid and not moving, like a chair, the particles inside it are constantly moving. They never stop moving. And they move randomly. They don't just move according to like very logical, precise rules. There's a huge amount of uncertainty to how they move, and they move in different directions, and it's very random, and there's whole fields of study into the motion of these particles, and we still can't fully explain it. So we just say that particles are in constant, random motion. Section 4 says that higher temperature equals faster movement. The higher the temperature of a material, the faster the particles in that material move. If you have a red-hot piece of metal, the particles in that are zipping around really fast compared to if that metal is cooled and left and it's quite cold. The reason for this is higher temperature means more energy, means more speed. These things are all correlated. Higher temperature means more energy, means more speed. Consequently, lower temperature means less energy, means less speed. If there's one thing you take out of this video, this is it. Higher temperature, more energy, faster. Lower temperature, less energy, slower. It's kind of intuitive, and even our own bodies kind of obey that in the sense that we speed up and heat up in the same thing, and we cool down and slow down. Those things are kind of correlated. And that's why people, for instance, tend to feel more lethargic, and it's harder to move fast in the cold. This is a molecular thing. It applies to every substance in the universe. Higher temperature, higher energy, faster speed. When we're talking about speed here, we mean the speed of the particles in the substance, which you can't see. But like we just said, all particles are in constant random motion. And this motion, the speed of it, is dictated by the temperature. And we have an intuitive grasp of what temperature is. It's how hot or cold something is. But there's quite a more precise definition, and we're going to learn about it in the next video. Particles at higher temperatures move faster than particles on lower temperatures because they have more energy. Remember that. And finally, number 5, particles attract each other. And we know all about this. There are bonds that form, and they really have all sorts of laws and things on how they attract and how they form compounds and so on. And we don't need to worry about any of these. This is a very general statement. Particles attract each other. Also, smaller the distance between particles equals a greater attraction. So there's another important thing to remember. The more closely packed these particles are in a substance, the greater the attraction. This makes sense. It's obviously a lot easier for instance, 2 magnets to attract if they're like right beside each other on your hand than if you have one on either side of a room. Less distance, more attraction. And this is really, the core concepts are just these 5. But the important part about the kinetic molecular theory of matter is not just that it exists, but that it explains real-life phenomenon. And I'm going to try and explain a few of them. The first one I'm going to explain is if you've ever walked around your neighborhood, you might notice that sidewalks, here's a sidewalk, have these gaps in them. There'll be a block of concrete and then like a little gap. And then another block of concrete and then another gap. And you might have wondered why. Is it just like for aesthetics? Do they just, want to create a pattern and that's what they chose? Well, not entirely. There's a practical reason sidewalks have gaps. And it has to do with the effects of this kinetic molecular theory of matter. We just said that in this rule 4 here, which is very important. Higher temperature equals more energy equals more speed. Faster, more energy, more speed. This has an effect on a substance, and that's quite important, and that it will actually physically change the size of that object. Because particles that are moving faster will tend to expand, and it'll go faster and, kind of become bigger and take up more space. And particles that move slower will start to contract, and they'll come closer together and kind of start to coalesce. And so the reason this temperature actually affects this change in kind of volume of these things, and that's why sidewalks have gaps. Because if not, the differences in temperatures between the summer and the winter would actually cause the sidewalk to crack. Because there'd be rapid changes in temperature that can't be controlled by the weather, and these particles would be changing speed, and the volume would be changing. You can't notice it, but ever so slightly. And so you would actually find that it would crack. And it's the same way that these kinds of gaps are built into all sorts of things around you, where it's very important. You might have seen cracked roadways before. It's because roads lack these gaps. They don't have them. And so you notice the cracks in them that form over time. It's because temperature is playing with the size of the roadway's molecules and kind of causing this like pushing and pulling. Second example here is a pipe. If you've ever seen a cold water pipe out, or even a cold pole or something cold, and it's a hot, humid day, you'll actually get condensation. It's what we call condensation, and it's these little water droplets that form on the outsides of the pole. And the reason behind this is, believe it or not, also the kinetic molecular theory of matter. And the reason this happens has to do with the states of matter. We're going to learn a lot more about them in the next video, but for now, just remember some basics. There's 3 states of matter that matter here. Solid, liquid, and gas. And as you go along them, solids are the ones that are most packed together, smallest radius. Liquids, a little more, and gases the biggest. This has very far spread apart particles. This has slightly less far, spread apart particles, and this is very closely packed particles. And so we can make this intuitive connection. Remember, higher temperature, more speed, and therefore less packed together. They're moving around, zipping around, etc. So this makes intuitive sense using something like water. Water is a liquid at normal temperatures. It's got particles that are kind of but not super mixed around, and they're, in between. When you heat water up by boiling it, you get gas, steam, because the particles have become excited, they have a higher temperature, greater energy, more speed, and they're expanding and creating this gas. And if you cool ice down or freeze it, you get ice. Less temperature, less energy, slower speed, more packed together. There's your solid. This is very important and explains condensation. Because on a hot, humid day, this cold water pipe is suddenly cooling the water droplets, the vapor that is in the air, and it's a gas, this water vapor, and it's being suddenly cooled by contact with this pipe. And when it's suddenly cooled, you get these droplets that form of liquid. It's changing state from gas to liquid because of the cooling down. And this phenomenon is due to the kinetic molecular theory of matter. It's explaining all these things. That's really all for this video. Just understand this theory and how it applies. In the next video, we're going to go over how thermal energy and heat work, and you're going to learn a lot more about this sort of application of the kinetic molecular theory of matter. Thanks for watching.